Approximately 3 billion people worldwide lack reliable internet access due to infrastructure challenges, economic disparities, and geographic isolation. Existing satellite and ground-based networks leave significant coverage gaps, particularly in remote areas where setting up traditional equipment is prohibitively expensive. High-altitude platform stations HAPS, which include uncrewed balloons, airships, gliders, and airplanes, offer a promising solution. These stations, positioned in the stratosphere, could enhance global internet connectivity, bridging the digital divide and enabling broader participation in the digital age. Electrical engineer Mohammed Slim Al-Wini and his team demonstrated the feasibility of providing high-speed 5G coverage from the stratosphere. Their experiment tested signal strength and reliability across different scenarios, including stationary, mobile, and maritime users. The results showed that HAPS could support high data rate applications like 4K video streaming, covering 15 to 20 times the area of standard terrestrial towers. Though early attempts by companies like Facebook and Google to deploy HAPS were unsuccessful, recent advancements and investments from traditional aviation companies and aerospace startups are reigniting interest. The goal of achieving global connectivity has earned HAPS recognition in the World Economic Forum's 2020 for Top 10 Emerging Technologies report. HAPS offers several advantages over satellite-based systems. They are faster, more cost-effective, and flexible. Positioned closer to Earth, HAPS can provide stronger, higher capacity signals for real-time communication, high-resolution imaging, and precise sensing applications. Additionally, they avoid the regulatory complexities and high costs associated with satellites and are easier to upgrade and maintain. Moreover, HAPS are potentially less polluting than satellite constellations. Satellites burn up upon re-entry, releasing harmful metals into the atmosphere, while HAPS can be powered by clean energy sources like solar and green hydrogen. Challenges remain, such as extending HAPS operational duration to months, boosting onboard green power, and ensuring reliability during automated takeoff and landing. However, their potential impact is significant. HAPS could play a critical role in emergency and humanitarian situations, providing connectivity when ground-based networks are compromised. They could also support IoT devices in remote areas, enhance agricultural monitoring, and contribute to environmental management, navigation, and disaster response. HAPS could be based on various aircraft types, each with its own advantages. Balloons offer stable, long-duration operation, airships provide maneuverability, and powered aircraft, including drones, offer precise control and power supply to communication equipment. Next-generation power sources, such as solar cells and green hydrogen fuel cells, combined with advancements in lightweight aircraft designs, are enabling longer flights and heavier payloads. Commercial deployment of HAPS for post-disaster or emergency situations could begin by the decade's end. For example, Japan has allocated $100 million for solar-powered HAPS to serve its remote communities. As technology advances, HAPS are poised to play a crucial role in bridging the global digital divide, expanding access to education, healthcare, and economic opportunities, and improving emergency response and environmental monitoring. They represent a key element in building a more inclusive and resilient digital future.